This should be the final part of the cutaneous senses, part 4, which will be the second part of talking about pain. And I typically do in class have people share some of the ways that they describe their pain, partly to get at that, the fact that oftentimes it is about the type of pain, the intensity of the pain. Sometimes they kind of sound like they're trying to describe things to their doctors because it's like sharp or dull or throbbing and what kind of pain it is. And I think of that as an intensity, or I've talked about it as intensity, but I'm also trying to pull out of people some of these more emotionally laden words where really we're describing the unpleasantness of our pain. We usually talk about pain as being unpleasant, frustrating, awful, all of those really emotionally connotative words. So talking about the multimodal nature of pain and the fact that we're seeing that really play out in different brain regions is a great way to talk about this Hofbauer et al. Study. So the multimodal nature being that there's a sensory component, so feeling my body, right? So the somatosensory, throbbing, hot, dull, those kinds of words that we might use that are describing the type of pain and the intensity of the pain itself, and an affective or emotional component of pain, where we might use, and they always have these great words sitting here for me that I kind of always forget, but annoying, sickening, torturing, or I might say torturous. And what Hofbauer et al. Did was they used hypnotic suggestion to decrease or increase each of those components. So both the subjective component of pain, the sensory component, and the pleasantness, or really the unpleasantness, right? This affective or emotional component of pain. And what they found was not only did this work, I can decrease and increase. So those conditions of decreasing are in blue, and the conditions of increasing with hypnosis are in red. I can either do this with that sensory component, so the actual intensity of the pain, and you can see that the ratings match what they were trying to do of decreasing or increasing. The other thing they find there is that there are changes in the somatosensory cortex, so S1. There are also changes in the anterior cingulate cortex, so that really emotional or affective component of pain. And then they also went and they increased or decreased the unpleasantness, so that affective or emotional component of pain. And you can see that what we see then in the ratings is that doesn't change the intensity, which makes sense. I still feel the same intensity. It's either more or less unpleasant. And then, but we could change the affective components, those ratings, and we can see again a decrease or an increase, depending on what the hypnosis is suggesting. And here, there are no changes in S1, the somatosensory cortex, which again makes sense because I'm not changing that intensity of what's happening at the body, but there are changes in the anterior cingulate cortex now. And so some of the regions that Hofbauer et al. Talk about really overlap with other regions that people have found as being part of this pain matrix of the brain, and really divvying out the job of this intensity or what's happening as far as somatosensory, me feeling my body. So if we look at S1, S2, and the posterior insula there in blue, that would be the intensity or my feeling my body. It's throbbing, it's hot, it's dull, it's sharp, that kind of thing. And the anterior insula, and then if you look at the picture on the far left, the dorsal anterior cingulate cortex, those are more involved in that pleasantness, unpleasantness. So when I'm sitting there thinking, hey, this is torturous, this is awful, this is debilitating, all of those negative words, we have activity in that anterior cingulate cortex that is basically telling me I'm unhappy, right? I'm really focusing on this unpleasantness. But it is also the anterior insula. Just so I match my brains there. And he does briefly address chemicals in the brain that are responding to pain. So this is the only time in sensation and perception where they really talk about neurochemicals. I've talked a little bit about ions, and I will say vision and hearing both. We release glutamate from those sensory receptors, but it typically gets a little bit ignored in sensation and perception, partly because there is so much. There's just so much to talk about with the psychological theories and philosophy all added in there. But those chemicals, the chemicals that we're going to talk about as far as what's influenced by pain, are probably some of the most important chemicals to talk about when we're talking about something like pain. So opioids that exist out in the world, like opiates and heroin, so whether they're actually from the opium plant or whether there's some kind of synthetic heroin or something human-made, are the chemicals that were discovered in the 1970s. And then this is the way this logic kind of happened with how we discovered a lot of our neurochemicals, a lot of the endogenous chemicals in the brain is, hey, we have these chemicals, these drugs that affect the brain in this way, and so there must be some kind of endogenous chemical that is behaving in a similar way or affecting those same receptor sites, those same neurons. And so then they discovered endorphins, where you might think endogenous morphine. So endorphin is coming from the endogenous morphine, our brain's natural opiates, and we can stimulate the sites in the brain that release these endorphins, and that's going to help reduce our experience of pain. They actually go and communicate. Those neurons go and communicate to transmission cells in the spinal cord. He also introduces this idea here of, or the chemical naloxone, which blocks the action of heroin or these different kinds of opiates. So this is what is in those injections, or now they have it nasally, where you can give someone this naloxone if they've had an OD on opiates, and it will pull them right out of that overdose, because what it's doing is it is fitting into, so we have endorphins, they fit into these receptor sites, they stimulate these neurons, they're going to go inhibit certain neurons. We have these opiates that also fit into those same receptor sites, right? So heroin, other opiates, they fit into the same receptor sites. They are agonists and behave as endorphins do, just exogenously, right? They're really just taking it in from outside of the system. Well, if we take naloxone, that's going to go and fit into those same receptor sites, but it does not stimulate the postsynaptic neuron. So these are known as direct antagonists. They go in and they can block heroin from getting into those receptor sites. The thing is because they're in there and they're blocking those receptor sites and they're not affecting the postsynaptic neuron, they're also blocking endorphins in the same way as it blocks heroin or other opiate drugs. It also is going to block the effect of any kind of placebo, because as we're going to see here in a second, placebos are basically, while we always thought of them as psychological, it turns out we are having a physiological response. We are. If we take a placebo for pain, we do release endorphins. In this excellent study by Benedetti and colleagues, they went in and did something where if this was a study I went into, I'd sign the informed consent and be like, nope, I'm leaving. I'm out of here. I'm not going to do this. I'm not going to be your participant, because this sounds awful. But what they did was they injected capsaicin. So capsaicin is that chemical that's in hot peppers that make hot peppers hot. They injected capsaicin into the participants' hands and feet. And then you can see for the no placebo group, what they did was just rate your pain on a scale from 0, no pain at all, to 10, extreme pain. And people are right around a 6, right? They're kind of varying around 5.5 or 6. So some amount of pain, a little lower than I feel like I would say, but that's okay. I haven't ever done that. So maybe it's not as bad as it sounds. And then, so they had another group of participants who received placebo cream on the left hand only. And so this is a cream that does nothing, but they're telling the person this is analgesic cream, and it's going to help keep the pain off of your left hand, and we're just seeing how well this works, right? So then what they found was those participants, they still were up around a 6 or so for those other limbs, other extremities, the hands and feet, but for the left hand, they were down at a 3.0, so lowered their pain very well. And part of this, I'm assuming this was to show that this is happening at the level of the spinal cord. So part of this idea is to, the next one is to see that we're not just releasing endorphins, we're releasing specific endorphins that are communicating to specific neurons, and we can even cross the spinal cord in this way because they went and they put this placebo cream, again, a cream that does nothing, but they're telling the participants that this is an analgesic on the right hand and the left foot, so on the opposite sides of the spinal cord and different regions of the body. And what they found was, again, in those two regions now, that lowered the pain, which suggests that, again, I'm not just releasing endorphins and, hey, having this brain response of I'm not in as much pain overall because I've released endorphins into the brain. This appears to be a very specific release of endorphins that then go communicate to specific transmission cells in the spinal cord. I go through all of that study and talk about that in that way partly because for me, I always wondered why does this have to go back down to the spinal cord? But that Benedetti study suggests that it does go down to the spinal cord. And again, these extra pictures, if it helps you to kind of see the pathway of I'm going up from the pain that's at the sensory receptors, and I'm going into the spinothalamic pathway, and then it's going to travel up contralateral to the thalamus, and then go to these specific regions, which I'm assuming it's too tiny for me to see, but I'm assuming they talk specifically about the somatosensory cortex and the anterior cingulate cortex, because those are typically the two main regions that most people talk about. But then we can also see, so those are the ascending pathways. We can also see these descending pathways from many, many different brain structures, one being the paraaqueductal gray, where we have lots of opiate receptors, so that I can go and communicate down from central control from the brain down to those transmission cells in the spinal cord. Again, not to memorize more, not trying to give you more. This is really hoping to help you kind of picture this. If it helps, that's great. If not, you can just, put your hand in front of it and not think about it, and that's fine too. I talked a few times in different classes and from different perspectives about these phantom sensations, about different how we have this experience of a phantom limb. If I'm missing something like my arm, people say that they feel like they're swinging their arm just like they would when they walk. So it's a phantom. They're phantom sensations, and something. At least 30% of the people, but now that I've seen a couple of videos, I wonder if I'm not misremembering that. At least 30% of the people have some kind of phantom pain in their missing limb. And so in this study, part of what they were trying to show with all of this is that there is part of what we're seeing is this brain reorganization. So if we go and we stimulate these 5 fingers and then the palm on the monkey, we can see these particular areas of the brain are responding to that. They went and they severed a finger or took a finger off of there, and then they went and stimulated what was the areas that were left, and you can see that the ones that were right around that finger. So if I take away finger 3, fingers 2 and 4, and these areas of the palm, those regions that are responding to those areas of the body, they basically grow into that area. And so I might feel if I push or do something on my my 4th finger, it might feel as if I'm touching my 3rd finger because it's gone, but that's the brain space that is active. People are typically kind of interested in this, and again, different books do this from different kind of directions. So in this, what they're showing here is this person has their entire left arm amputated, or it's gone, and you can see that now touching up on the shoulder makes him feel like he's being touched on those digits. Same with being touched on the face. And if we look at the somatosensory cortex, that homunculus, and how that body map is laid out, you can see that what I'm missing is my hand and my lower arm. And so what's going to grow into that? Well, the face and the upper arm are kind of the surrounding regions. And so they're going to be taking up more cortical space. Those neurons don't want to just go silent. And there are going to be times when we touch one of those regions and it's going to feel like it's happening on an arm or a hand that's still there. I don't plan to require this video, but this video is in your PowerPoints if you want it. It's a really neat video with R.S. Ramachandran. He was the person who came up with the idea of mirror therapy. So one of the things they discovered for phantom limb pain is that if I'm missing, let's say, my left arm, I can put a mirror down, show my right arm, and if you massage my right arm, it looks like you're massaging my left arm, and it feels to some extent like you're massaging my left arm, which is no longer there, right? And so because you're massaging something that's no longer there, you're not getting the inhibitory feedback that's saying, hey, nothing's touching you there. You are getting the excitatory feedback from your sense of vision. And so if you remember, I can close the gates of pain by doing that rubbing, or so massaging helps, and we can relieve some of the phantom limb pain. The author has added some of this, the end of social aspects to pain. It looks like what I've really decided to do, and I think I'm going to shorten it a little bit, is just talk about some of the different social situations where we see pain. And a couple of my favorite studies, one comes from Tanya Singer and her colleagues, where partners come in and either the woman receives the shock herself, or and both of these, the female is put in the fMRI, or she's just watching her male partner receive shocks. And so when they're receiving the shocks themselves, there's activation in the somatosensory cortex and in the those affective emotional component regions like the anterior cingulate cortex and the insula. But when they are watching their male partner receive the shocks, there's still activation in the anterior cingulate cortex and the insula, but not activation in the somatosensory cortex, which makes sense that I'm not actually feeling that in my body. My empathy is not quite to that degree, but I am having those same or similar seeming emotional reactions as far as my emotional affective components of the brain that are responding to pain. So the anterior cingulate cortex and insula are both active to just watching someone else be in pain. And Singer and colleagues had those women fill out empathy scales measuring their tendency to empathize with each other, with other people, and their empathy scores were correlated with that activity of the anterior cingulate. So the more highly I am rated on empathy, the more activation of the anterior cingulate cortex. Just because it was too much for one slide, here are the pictures. So receiving the shocks myself, you can see on the left, there's lots of activation in many regions of the brain. Watching my partner receive shocks, there's still activation in certain parts of the brain, specifically the anterior cingulate cortex and the insula. Another example of pain in a more social sense or in a social situation is this feeling of distress. And they've caused this feeling of distress in a number of ways. One of the most famous ways now is this cyberball kind of research where Naomi Eisenberger and her colleagues started this cyberball game with people who are, so you're in the fMRI, you're watching these two people throw a ball back and forth on the screen, and then you're included in the game. and they continue to measure your brain activity, and then those two other people exclude you from the game. My understanding is some of these are actually people, some of this is just computer programmed. It depends on the study. But so what happens when and so the person in the fMRI is under the presumption, right, that they included me, and then they decided for some reason to exclude me. And so that social exclusion can cause a great deal of distress in people. And what they found was there were regions of the anterior cingulate cortex that were active in this distress or social pain, similar to what Tanya Singer and colleagues found when we were feeling empathy for someone else. And what that correlation, or what that figure on the very bottom right is showing, is that the amount of activation in the anterior cingulate cortex for these people was correlated with how highly they rated, or how high they rated their distress, right? So how much distress am I experiencing? With the more distress that I'm experiencing, the higher the activation of the anterior cingulate cortex. I have taught this class since 2012, and I know you probably are aware of the fact that when we're working from a textbook like this, they come up with new additions and then they include new research, but a lot of times that research, by the time the textbook gets published and everything's, said and done kind of thing, that research is at least 2 or 3 years old. And so I taught this for a long time, talking about Eisenberger studies and really convincing myself that, hey, we have this overlap, this physical pain / social pain, physical social pain overlap. So that became later in 2014 more of a hypothesis, and then how this is happening or how this works came under a lot of scrutiny when Wu et al. In 2014 used this multivariate pattern analysis, which, because we skipped some piece of vision where we were talking about, where we looked at neural mind reading and looking at different scenes that are out there, and the fact that I can start to predict what kind of scene you're looking at, we skipped multivariate pattern analysis, but it takes a much more fine-grained examination of the brain activity when someone's in an fMRI. So a lot of times we're just looking at the brain activity in a structure. We can look at brain activity in really small structures, but what this is doing is taking a, if you think of a cubic pixel, so these pixels by pixels on our screen, but make them cubic and 3-dimensional pixels. Now we're looking at specific patterns of neural firing within those brain regions, right? Sometimes it's like they look at something like 1,000 different single cubic millimeters to look at the pattern of activation. So that's what MVPA is. And so Wu et al. Went in, they had people thinking about or recalling a social rejection from a romantic partner, and then they also had them feel a painful heat on the forearm. And what they found was that there was some overlap, but that pattern was not as much, it wasn't an exact kind of pattern match. There was some overlap, but the question now is how much overlap is there really? And does this mean that these are the same things? Because they talk about, sometimes people talk about the cingulate cortex, or that area of the cingulate cortex, as being a salience network. So something that is salient, that I'm paying attention to, or is grabbing my attention. And so if we're seeing different activation, I mean, maybe it's still salient to me, but it's not the same as physically being in pain. And so now they're still really disentangling and teasing this apart so that they can figure out better what is the physical social pain overlap. And I am going to end here. This video is running a little bit long, but I think I got us to about our hour and 40 minutes. In the something to consider section of this chapter, he talks about the plasticity of these body maps, which I did a tiny bit when I talked about the phantom limb. But another kind of study that came from Jenkins and Merzenich was a study where they were being stimulated on their finger. Before experiencing a great deal of stimulation, they went and stimulated and just measured what part of the brain is active. And you can see that in the top map, that second digit there, I have a little bit of activation. But then I go through this training, right? I'm using that stimulation in some kind of task. I'm getting stimulated over and over again. And then afterwards, they go and they do the same measurements. And you can see for that second digit, the amount of brain space that is responding to stimulating that second digit has grown. And so we just see, it's another really good example of experience-dependent plasticity. So two of the things I think are really important to think about for sensation and perception in general is that I have to pay attention for the cortex to be activated. And so it is attention that is influencing this conscious experience of my world. The other thing that I think is really important to remember is that we do have experience-dependent plasticity. Our brain changes and molds depending on the experiences that we have. And so it's good to remember to choose positive, good experiences that can help the brain to wire in healthy ways.